Hey guys, so this is a follow-up video to the video on integrals. Um, one thing in particular, just an interpretation of integrals, and then I'll talk about one other thing called an improper integral. And right, so all this is, right, we looked at the definition of an integral in terms of a sum, and what we saw is if I've got a function, any function, it does, and I want the integral from here to here, right, from a to b, I'm summing up a bunch of really small rectangles. The integral is like a continuous sum, right? So if I'm summing up an infinite number of things, but I'm summing them up continuously, right? So integral of f of x dx from from a to b is a continuous sum, right? It is the area, right? But it's really a continuous sum of f of x from a to b, right? And if we summed up every point without the little interval, this little dx, that would sort of blow up to infinity. So this dx is sort of what keeps us sane here, what makes this sum actually be able to exist. But it's a continuous sum of f of x from a to b. Now, one other thing we've got, and this is just basic, an integral can sort of be thought of in a general way as just the generalization of a sum. Right, so this is just a way to think of the integral, and we're going to come back to this in quantum mechanics again and again and again. Okay, so the last thing, I just want to make this a quick note, is something, it's pretty easy, it's called an improper integral. And there's a few different types of improper integrals, but what we're really going to be using is if I've got like an integral from negative infinity to infinity, right? That's going to be if I've got a function, and for a function for this integral to exist, it's got to go to 0, right? If it doesn't go to 0, if it doesn't asymptote at 0 or hit 0 for good, this sum may not converge, right? It may blow up. And even if it does, go to 0, it could still blow up, and but that's a bit of mathematical nuance, and you can look in the description. I'll have some links on that. But really, what I just want to focus on is if I've got f of x dx, right? I'm finding the area between negative infinity to infinity. If this area exists, right? Well, according to the fundamental theorem that we talked about, right, or just the fact that we have this, integral function, this indefinite integral function, this is like capital F of infinity, minus capital F of negative infinity. That doesn't really make sense, just because, you can't really plug in infinity. So what we have to do, and hopefully you're familiar with limits. If you're not, I had you on the when we were talking about derivatives, look up, if you aren't familiar with limits, or if it doesn't just make intuitive sense, it's a way to just approach something to see how something approaches something else, and get an answer, even if even if it looks like 0 over 0, if you plug it in, if you go calculate a limit, you may actually get something that as you approach that value, even if at that value it's like 0 over 0 or infinity, or if you approach that value, you might actually get a finite answer. So how do we do that? Well, we can't plug in infinity, we can't plug in negative infinity, but we can plug in a limit. So this would be the limit as x approaches infinity of capital F of x, right? Then minus the limit as x approaches negative infinity of capital F of x, right? All you need to do is this limit, and that's it. It's just a limit. And I just wanted to say this so you can understand that there is this thing, and we can do this. Some functions, such as, right, maybe not negative infinity to infinity, but it is indeed true, right, that the integral of the function e to the x, right, e to the x looks like this, right, and it asymptotes at 0. And if I want, say, asymptotes at 0, it's a really bad drawing, but you got the point. If I want the integral from negative infinity to infinity here of e to the x dx, right, well, right, if I want that, that's the area not negative infinity to infinity. This would blow up because there's an infinite area over here. But maybe from negative infinity to 0 will not be infinite. Maybe, right, this from negative infinity out to here, out to 0, it goes to 0 really fast. Maybe there's a finite area, or the limit of that area as you get farther out to negative infinity will be finite. And let's see. Well, maybe you don't know how to do this right now, but we will soon find out how to find, right, if f of x, right, f of x here is e to the x, right, capital F of x, the integral function, is actually e to the x plus some constant, right? But when we do this, right, this is, right, capital F of x evaluated at negative infinity, right, and a capital F of x evaluated at 0. When you subtract the two, the constant goes away. So we can actually ignore this constant. If we have bounds of integration, we can ignore the constant. So this is, right, the limit as x approaches negative infinity of e to the x minus, right, did this backwards, apologize. This is e to the 0, right, e to the 0, because you don't need to take a limit. E to the x is defined at e to the 0. You don't need a limit. Some functions, like there's a non-infinity thing that the function will be not defined at, and you can sometimes use a limit for that. It's another type of improper integral. But for right now, right, we've got this e to the 0 minus, right, the limit as x approaches negative infinity of e to the x, which is, well, as I get closer and closer to negative infinity, e to the x, right, if we look at the graph of e to the x, as I get closer and closer to negative infinity, it gets closer and closer to 0. So even though it never will hit 0, as we approach negative infinity, this limit is 0. So this is e to the 0, which is 1 minus 0, right? So it turns out this area, and no, it's not necessarily the case that this capital F of x is the same. It just so happens with e to the x. One of the things that makes e so special. But this area under here of e to the x from 0 to negative infinity is equal to 1. It's an area from negative infinity to 0, but the limit of that area as we get farther out to negative infinity is actually equal to 1, which is pretty cool. So that's that is improper integrals. Hopefully that makes sense, and hopefully we've got it down. Yeah, I mean, that's pretty much it for, just knowing how to express, how to think about the integral in terms of a continuous sum, and also knowing that you can sum from, negative infinity to infinity or negative infinity to 0 and get an actual answer for that area. Just depends on how fast it will get down to 0. And hopefully this makes sense, and hopefully it makes sense. I mean, that's really what I'm going for right here, to make sure it gets sense so we can apply it later in quantum mechanics. And if it doesn't, I've got some linked videos. I'm trying to do these introductory, background videos pretty fast, because that's not really the focus of this course. So I'll have other videos available for extra help. I'll see you in the next video.